This video explains how to use my solar battery calculator. The calculator is geared towards small to medium system battery backup systems. Your recharge source can be either solar or a generator or the grid. So if you are a do-it-yourself kind of guy who needs some guidance on how to size up the components of a battery backup system, this will fill in that information. If you want to jump to a particular worksheet or design option, then here are the timestamps. The calculator is an Excel spreadsheet that can be imported into Google Docs if you don't have Excel. At the bottom of the worksheet, there are comments explaining each cell of the spreadsheet that say most of the same things that I'll be covering in this video. If you don't already have the spreadsheet, you can download it from Todd Sepulveda's Prepper website. Copy the link seen here, or you can find a link labeled Solar Battery Calculator on prepperwebsite.com. To size a battery system properly, you need to add up all the loads you plan to run and how long each load is going to be on for a 24-hour day. That gives us watt hours total we can plug into the calculator. The first worksheet of the spreadsheet is to help you figure out the total watt hours loads. It allows you to figure out the load from one of 3 different methods for each item. The rightmost column lists all the individual watt-hour loads. The lower right corner is where everything is added up. Under the watt-hours column, the total watt-hours can be found. To the left, you'll find a recommended minimum inverter size for those loads. If any of the loads are primarily motor-driven, like freezers, refrigerators, pumps, or air conditioners, then in-the-rush current has to be accounted for, so the inverter size is bumped up if yes is selected. Let's look closer at each column, starting at the top right of the sheet. The rightmost column lists the watt hours of the items that our solar battery systems needs to power. To the left of that column, the watt hours per day can be entered directly if a kilowatt or similar meter has been used to measure the power usage over a 24-hour period. The right column will automatically be populated from the available data. If the watt hours are not known, but the watts are known, then the device wattage is entered under the watts measured column. Then estimate the hours that the device will be used each day and enter that here. The third column will automatically calculate the watt hours, and the rightmost column will automatically be filled in. If you don't have watt hours or watts, but you do have the amps that the device draws, then enter that here. The watts will automatically be calculated, then enter hours of use per day as before, and the rest will automatically populate. The main calculator is broken down into several zones. All the dark blue cells are for data input. Most are in the input section with a few outside. Because there isn't a one-size-fits-all design, this calculator lays out 4 different designs. The first costs the least. The second makes full use of the battery before any recharge. The third is geared for off-grid solar. The fourth design starts with a particular battery size and works out from there. One of these 4 designs populates this block depending upon your priorities. That data is then adjusted for the number of cloudy days in this block. Each design, input data and output data cell are described below in the corresponding design. Now let's take a closer look at the input section. The inverter, charge controller, and battery type have power losses that change depending upon which type component is used. A cheaper low-efficiency inverter will result in a larger, more expensive battery and solar panel selection. Appliances with large motors like freezers, refrigerators, sump pumps, well pumps, or air conditioners have very large initial inrush currents. So if with motor is selected here, then the inverter size will be rounded up to compensate. Budget inverters generally do not handle motor inrush currents well and need to be sized up to not trip them into shutdown. So premium sine wave inverters will be rounded up 900 watts and budget sine wave inverters will be rounded up 1300 watts. Budget inverters generally cost less than 50 cents per watt, and premium inverters start around 70 cents per watt. And I particularly like the Xantrex Pro sign. Load hours per day means how many hours per day will the appliance be plugged in and turned on. The lower this number is, the more accurate the low-cost inverter size calculation will be. Generator runtime is subtracted from the load hours to end up with the number of hours that the inverter battery must supply the power. If you know how many watt hours you need from the solar battery system, enter it here. If you use the Sheet 1 calculator, then change this link to Sheet 1 to have its watt hours auto-populate into B11. Sun hours is a value used to figure out how much power a particular solar panel array will put out in a day. Sun hours is not the same as daylight hours. If we combine all the remnants of the solar panel's partial output so they amount to a shorter time of full solar noon output, that equivalent full output time is the sun hours rating. So we use that number, sun hours times solar panel wattage equals the solar panel's watt hours of output per day. So find yourself on the map and enter the corresponding sun hours into cell B12. If you don't plan to connect a 120 volt battery charger to the generator or the grid, then change this to no charge. Otherwise, leave it at max charge. For lead acid, the solar panel charge rate and the 120 volt charger are both defaulted to a 10% of the battery amp hour capacity. For lithium, the charge rate is twice as much at 20% of C. If you plan to charge your lithium battery at some rate other than the normal 20% C, then you can change that here. For example, if you have a 100 amp hour battery, then the default charge rate is 20 amps at 20% C. If you select 200% of max, that would mean you're going to charge at 40 amps. Some lithium batteries can handle even more than this. This box allows you to pick one of 4 design options that populate the cloudy day calculator to the right. The first design option minimizes the battery and inverter size. Minimizing the battery will often result in the need to recharge a battery while it is being drained and not wait until after it is drained. Since this is the normal way we use solar battery systems during the daylight hours, it only poses an inconvenience after dark when you may need to intermittently start the generator. A small inverter will work in most situations, but it's also much less flexible in taking on unplanned loads. The lowest cost design is in the lower left corner of the worksheet. The solar panel size should not be exceeded. If the closest panel size you can buy is larger than this, then increase the needed watt hours in cell B11 until the solar panel watts agrees with the wattage of the panel you plan to buy. This will make sure the battery and the charge controller size are in line with the solar panel. Panel voltage can be anything that meets the charge controller's input requirements. The charge controller regulates the voltage applied to the battery. Charge controllers are protected by limiting the solar panel size on their input side and are rated in amps. So a 30 amp charge controller can handle up to 30 amps between the charge controller and the battery. The 120 volt charger is what you plug into the generator or a grid. The amp hour rating of the battery is derived from the charge current and the battery type. You probably can't get the exact battery size specified here, so round the battery size up to what is available. You do not need to adjust the size of the other components, but if you want to take full advantage of the larger battery, then increase the needed watt hours in B11 until the specified battery size here matches the larger available battery. This design emphasizes the lowest cost, and the inverter is one of those elements. This minimum inverter size may not work for all loads that draw a lot of power for short periods of time. If load type in the input section is set to with motor, then additional watts are added to account for inrush currents. This inverter size calculation is much smaller than the rule of thumb calculation used in Design 2, which allows for more expansion and unpredictable loads. It would be a good idea to install a larger inverter if you would like more load flexibility. Use Design 2's larger inverter size as a maximum. If you link to Sheet 1, then the inverter calculation from Worksheet 1 will be used instead. This is almost always a smaller inverter. This inverter size has no room for expansion, but is the cheapest option. DOD, or depth of discharge, is how far down the battery is drained. For lead acid, which includes flooded RAGM, should only be drained 50% or less. If you drain a lead acid battery below 50%, it will not immediately be apparent that you've degraded the battery, but it will take some time off the life cycle, so it won't last as many years. And in a worst case scenario where you drain it down to where the inverter shuts off and then charge it maybe with a truck charger that's way above 10%, you could damage that battery to a point where it's only good for a couple weeks. If this value in this cell is greater than 50% for lead, then you will have to do some charging while it is being used. For lithium, the maximum depth of discharge is normally about 90 to 100%. If there just wasn't enough solar or charge hours to recover a battery, some additional grid or generator charge time will be required. This value is the total number of hours needed to recharge the specified battery. The estimated battery cost. Since the battery is usually the most expensive component in the system, this gives a hint about what it's going to cost the entire system. The overall cost will be several times the cost of the lead acid battery, and lithium costs about 5 times more than the lead acid per amp hour. If weight is a concern, then battery weight will allow you to compare lithium to lead. Input the wire length here. That includes the length of wire to and from the charge controller or inverter. So if the inverter is 2 feet away from the battery, then it will need 4 feet of wire. The American Wire Gauge, or AWG, size for copper wire is calculated based on the peak amperage, system voltage, and wire length. So don't use aluminum or copper-clad wire. Be aware that some copper wire sold on Amazon is copper-clad. That is, it's aluminum wire with a thin copper coating. Design 2 sizes the battery so the full load will cause the battery to drain down to the maximum depth of discharge and no more. This is useful when wanting to use the battery at night to run a few loads, then recharge after the sun comes up or when the generator kicks back on. Or maybe you expect the grid to be down for just a day and you will recharge from the grid after it comes back up. Design 2 is located here. There are 2 differences between Design 1 and Design 2. The primary one is that the depth of discharge is set to not go below either 50 or 90% depending on your battery type. The depth of discharge can be changed. Changing it to a smaller percentage will result in a larger battery and faster recharge time. A higher value will require the battery to be charged some during the load day. After that's locked in, the rest of the system is built around the battery size. The higher of the 2 inverter sizes is derived from the rule of thumb battery amp hours times 9. This inverter size gives a lot of flexibility for various loads, but will cost more. The lesser value is copied from Design 1. The builder has to balance load flexibility with cost when sizing the inverter. If your loads are fixed and unchanging, then you can get by with a smaller inverter. If you don't know what you might be plugging into your inverter, then size the inverter closer to the larger value. Keep in mind that if you constantly use all the wattage of the larger inverter, your battery will be dead in about an hour. Design 3 is geared towards off-grid solar systems and will attempt to recharge a battery by the sun only. Design 3 is located here. Design 3 figures out the solar panel size that will produce the needed watt hours within the sun hour period of time. So unless you live in Western Washington, then you should be able to recharge your batteries by just solar. Since a lead acid battery usually ends up being twice as large for this design, The normal battery-based rule of thumb for the inverter calculation would result in an inverter that is twice as large, which would be much bigger than you need. So, Design 2's inverter calculation is inserted here. The minimum inverter size option is borrowed from Design 1. Again, the builder has to balance load flexibility with cost in sizing their inverter. The very low depth of discharge is achieved by a much larger battery bank. The large bank means the charge current is much higher, which is how it is able to recharge faster within the sun hour time. If sun hours is 3.5 hours or less with no generator time, the battery bank would be impractically large to get it to recharge within 3.5 or fewer hours. So the battery bank size is limited, and the remaining time needed to recharge the battery is noted here in this cell. This is the recharge time to recover the watt-hour load defined in the input section. If it is a rainy day, this is how many generator hours are needed to recover the batteries. This is adjusted for the battery type. Two inverter wire gauges are spec'd to correlate to the two inverter options, the right for the larger inverter and the left for the smaller inverter. Design 4 is a tool for figuring out what size solar panels and charge controller would work with a given battery size. This is useful when you want to build around a particular battery bank like a golf cart. Design 4 is located here. The first thing to do is enter the amp hours of your battery. Then the inverter size is calculated using the battery amp hours times 9 rule of thumb, although a smaller inverter could be installed if you know what the maximum load is going to be. Charge amps and charge controller are figured out next, then the solar panel size. Solar battery systems must also work on rainy days, so this last section is used to figure out how much larger the solar battery system needs to be by first copying the values of the design that meets your priority. The priority design values are then multiplied by the number of cloudy days to resize the system. Depending on which design is selected by the priority drop-down box, the applicable data is migrated up to the cloudy day baseline table. The cloudy day system size is displayed to the right. The left matrix is the priority design. The right cloudy day matrix has two data entry cells. Enter the number of cloudy days you want your system to continue to operate here. The solar, charge controller, and battery size are multiplied by the number of cloudy days, so you can see the system gets much larger very quickly. If the resulting system size is too costly or large, then you can supplement the cloudy days with extra generator time. The resulting system takes into account that the generator will be taking the load and charging the battery at the same time, so a generator hour works out to be more than a one-to-one replacement for sun hours. Notice inverter size is not changed from the priority design value because the peak wattage on a cloudy day is the same as it is for a non-cloudy day. Also note that if two inverter values are specified in your priority design, only the larger of the two are moved up, but you can still use the small inverter size if you understand your load. The fourth page is a tool for sizing the wire for a given amperage, wire length, and battery voltage. Wire length includes the run to and from the load, so if there is 10 feet between the battery and the load, you enter 20 feet. Battery voltage needs to be a factor because a little voltage drop has a much greater effect on low voltage devices. The overall voltage drop is limited to about 3% of the system's voltage. That's it. I spent over 60 hours piecing this spreadsheet together, so I hope you find it useful. God bless you in your self-sustaining endeavors.